the hard margin classifier or hard margin SVM will not work. So what can work is a soft margin can work, but soft margin again has its limitations in terms of how many points or how many points can be there in the pipe, right? Okay, and you cannot indefinitely expand, keep on expanding the margin, right? So because as you expand the margin, there'll be more points that are possibly misclassified, or the training error will go up, right? So we have a penalty term in the objective function, and we change the constraints in a way that we become a little bit lenient. We don't want that all the points should be within a distance of 1, right, as we have done. So we say that they can be 1 minus epsilon we introduce, right? Okay, so that's the change we do in the formulation for soft margin. I'll come to that. Now the most generic thing is that without worrying about whether data is linearly separable or not, right? Like the one here that you see. Okay, so here the data is not linearly separable.
Sir,
so you'll not. Yeah.
You are not presenting, so.
Oh, is it? Oh, okay. Just give me a minute. Okay. I think I started the recording, but not the presentation. Just give me a minute. All right. Share screen. Yeah. Yeah. So can you see now?
Yes, sir.
Okay. So this is what we were discussing towards the end, that you have a case of red and blue points which is not linearly separable. So do I try to fit a soft margin? So the question is that whether I fit a soft margin SVM or I should go for the nonlinear SVM, right? So this is the question that I have to answer, right? So in this case, you see that fitting a soft margin SVM may not make much sense, right? Okay, because we can see that where do we draw the line? Okay, so it is not very kind of intuitive to use SVM. Another important thing is that you will not always have your problems in 2 dimensions. So your data would be in very high dimensions. So you'll not have the luxury of visualizing your data, right? So it will be very difficult for you to, and even if you are able to visualize, you cannot go beyond 3 dimensions, right? And then you do some projections, but getting a good idea whether you should use a soft margin or non-linear, or whether the data is linearly separable or not. So these things are very, very difficult, right? So I told you in the last class that you start working with the hard margin, and if it gives you good hard margin, if the data is not linearly separable, it will not give you a solution, right? So then you have to move to soft margin, and then finally to nonlinear SVM. So in the case of nonlinear SVM, as you can see here, so this is the curve that I'm getting, right? So this curve, and again, how many such solutions are possible? How many solutions are possible?
Infinite.
Infinite, right? So that's correct, because I can have different shapes, right? So I can have a shape like this, right? Or a shape like this, right? Or shape like this. Okay, yeah, here. So I can have infinitely many solutions like we had in the linear case, right? And again, I have to figure out which one is the most optimal, right? So like the same problem we faced for the linearly separable data, or the linear SVM, right? Okay, so so the same questions we need to address, right? So again, we'll talk about the same kind of questions. So one approach that we take in nonlinear is that we transform our data into a high dimensional space. Okay, So you're transforming your data into higher dimensional space, right? And when you do that, right, you get a linearly separable solution. Okay, and we know how to work with linearly separable solution, right? Okay, so now what we are doing basically is that you are taking a nonlinear transformation, right, from, okay, and you get something in what we call as the feature space, right? Okay, so this X is basically your, it is in the input space. So I'm introducing some terms. So you have what is called as your input space, and you have something called as your feature space. Okay, so input space means the data that is given to you. So like in the previous example, in the example that we are discussing, so it was a 2D input space, right? And your feature space that was taken, it has to be greater than 2, right? So you can move to 3, 4, or any higher number. Okay, so you move to a higher dimensional space, and here you can see that I'm showing you only 2 dimensions, right? So one is this one, so you can see that this is not x2, and this is only x1, right? So I could have, so I'll show you some transformations, some typical transformations that we carry out. But first you try to understand that what is happening. So you take the data from a lower dimensional space to a high dimensional space. And if you recall our discussions on curse of dimensionality, right? Okay, curse of dimensionality. So when you move to high dimensional space, you are facing problems related to curse of dimensionality. All right. So does it make sense, or is it a good idea to be doing all of this, right? Just because you want a linear separability between the data, right? So these are some questions, right? So I want to move to a high dimensional space because in that space my data would be linearly separable. That is the incentive for me, but I have to also deal with the curse of dimensionality problems, right? And here we'll be looking at one aspect of curse of dimensionality problem, and that is the computations. Like if you recall, right? So in the SVM formulation, there is, so I'll talk about that now. So in the formulation, you will see that there is a need to compute what is called as the dot product between 2 input vectors all the time, right? Okay, so I'll talk about Lagrangian formulation of the problems. I'll start with linear one and then move to nonlinear. So one of the requirements is that you have to find out x1 dot x2 for all pairs. So I'll write it as xi dot xj, all right? And for all pairs of I and j, right? And what does this tell you? So if if x's are vectors in some input space, so what does xi dot xj tell you? What does it give? Yes. What does it give you? You know the dot product or the scalar product? Yeah, anybody?
Sir, area of parallelogram.
Not
Formed
that.
by these 2 vectors.
Sorry?
Equation of the hyperplane.
No, not the equation of the hyperplane.
The representation of the vector in another one's direction.
No. See, what does it do? Look, let me explain this. So suppose this is one vector x1, right? And this is another vector x2. Okay. So x1, suppose it has 2 components, x1 and x2. Okay. and this one has two components, x3, x4, right? So what does the dot product between those two vectors indicate? Yes.
X1, X3, and X1,
Similarity.
yeah.
Yeah. So it basically it is also called as the cosine product, right? Okay. So I'm not asking that what will give you. It will be x1, x3 plus x2, x4. That is all right. But what does it indicate? Right? It basically indicates how similar these two vectors are. Right? Now suppose they are. So it is also called as the dot product, right? So the cross product, no, not sorry, cosine similarity, right? So this is about the angle between them. All right. So if the angle between them is less, say suppose my x1, x2 is like this, right? So the angle is smaller, right? So the dot product would be higher, right? Okay. So like this. So basically, the dot product tells you how similar two vectors are, right? Okay, how similar two vectors are, right? So this is a very important calculation that you do for all the pairs that are there in your data set. Now, in case we have done this transformation, right, from the input space to the feature space, right? So let me show you another. Just yeah. Okay. So let me do it here. So earlier, when you had not transformed you were doing this. Now you have carried out the transformation, right? And then this. Now you have moved into the feature space. So this was input space, and this is your feature space. So whatever you were doing in the input space, the same thing you have to do in the feature space, right? So you can see feature space is high dimensional and input space is low dimensional, right? Okay, so your amount of computations go up when you do this. All right. Okay, so in the feature space, the amount of computations go up. So what we do is, like I've already introduced margins and duality. So now I'm going to talk about kernels. So now there are some special kinds of functions that we can use. And there is a kernel trick which tells you that, I'll write down this here, xi dot phi xj is equal to k times xi, or not times, xj. Okay, so what do you understand by this? So this is a very, very important aspect of SVMs and kernels, right? So what do you make out of this particular expression that I have written here? What is the main thing in this?
So we are transforming the similarity into a linear or equation on these two vectors.
Okay, so like let me explain this. Let me give you some hints. I'll not give you the answer straight away. So now, once you are in the feature space, right? So you have to calculate this, right? All right. This is what you have to calculate. In the input space, you are calculating this. Is it not? Right? Because this comes under, as I said, this is the main calculation that you do in SVM, xi dot xj. Right? You'll see where we do this in a while. But let me give you the concept first up. So in the feature space, I'll have to do this. And this is, since this is done in a higher dimensional space, your amount of computations are going up. But now I am telling you that there exists a function. please, there's a lot of background noise. You please mute your mics. And then when you have to ask a question, then only you please unmute yourself. Okay. All right. So I tell you that there is a function, or right, there's a function k which does something good here. So what it does is that this dot product in the high dimensional space is now converted into a calculation which does not involve phi, which is in the input space itself. So calculations in feature space gets converted into calculations in input space. Input space, again, as I said, you know, it is a low dimensional space and feature space is high dimensional. So I am now able to transform or do all the calculations that are required in the high dimensional space using calculations in the low dimensional space or the original space or the given input space. All right. So these Ks, right? There are many different kinds of Ks that you can find. These are actually called as kernels. And this particular thing is called as the kernel trick. All right. So are you getting some idea? I'll talk about kernels in a while, right? Okay. So something like this is possible, although there are certain kinds of conditions.
Excuse me, sir.
Yeah.
Sir, could you please give an like a sort of 2D to 3D example over here?
Yeah.
I'm not able to get it.
I'll come to that. I'll have to open up another presentation, so I'll do that today, right? So just wait for a few minutes. All right. So let me now take you. So I'll skip these slides. These are not directly. Okay. Okay. Let me take you to the formulation part, right? Okay. All right. This we have discussed, hard margin, soft margin. Oops. Not this one. Yeah. All right. Okay, let me just switch off the presentation. Okay, end show. I'll have to scroll up. I'll take you here. Yeah. Just give me a minute, right? Yeah. So you can see here. So can you see this? Right. This is the formulation of SVM, right? Okay. All right. And at the bottom, you see this, that this is a. So let me use a color which is not used as. Okay. Just hold on. Oops. Yeah. So let me use what color should I use? Okay, let me use a green color. Okay. Yeah. So what you see here, I'll blow it up a little bit, or if you want, I can write it separately also. I'll do that after this. Just let me show you this. So all of you understand this part, the formulation part, the objective function here. So I'll put a tick, right? So this you know, and these are the constraints here. All right. Okay, and there are n training points. So these are n constraints. Okay, so now what I'm doing here is I am formulating this using Lagrangian multipliers. So all of you know Lagrangian multipliers, the method of that. So it takes the objective function here minus the summation over all the training points and lambda I, and then you have these constraints. So w dot xi, right, plus b minus 1, these are the constraints, and all the constraints are there. So this is what is my primal formulation of the optimization problem that we have at hand. Okay, this is what we need to solve. Right. So now what I do is, so let me take you to the next slide. Yeah. So LP involves large number of parameters. It involves lambda I, it involves W, and it involves P. Right. So what we do now is we convert it into a dual problem. Right. And we have already discussed that converting to dual, right, is or the dual has the same solution as the prime. But sometimes it may happen that, right, it may happen that the dual is a simpler problem to solve as compared to the prime, right? So if you see this, this is the dual formulation. So there should be a double summation here. I mean, right? So, I mean, we don't write double summation, but just to make it clear. So it is lambda I, lambda j, okay? And yi, yj, these are the classes. And then you have this xi dot xj. So you have to do this how many times? You have to do this n square times. Are you able to see this? Right? Because there is double summation. But now you see one more thing, that here there are only lambda i's that are involved, right? Okay, and W and B are not there in this formulation of the dual, right? So what we are saying is that LD is simpler than the primal. The dual is simpler than the primal, and as it involves only lambda i's and the training data, which is xi dot xj. I mean, which is coming in the form of xi xj, although the classes are also coming. Yi is the label of xi and yj is the label of xj. Okay, so we do this. So that is where xi dot xj is coming in the formulation. All right. So now, okay, is that clear? All of you see that where from this xi dot xj is coming, right? So it is coming in the dual formulation of the problem. Okay. And now let me tell you one more thing. Okay. So if you take you back, so if I replace xi, okay, let me use a different pen. This is not very visible. Let me use this. So, okay, so whenever you have xi, right, and you replace it by phi xi, right, so you get the corresponding nonlinear formulation. Okay, so that's the only change you need to carry out. All right, so keep this in mind. I'll use it later. All right, so now I have this. So you know that in case of nonlinear, what this would look like, the dual would look like the same thing, but here I'll have phi xi and phi xj. That's the only change that you will see. All right, so now let me give you some idea about the kernels, and as somebody mentioned, that if you can see a kind of a example, right? So I'll have to end this show and this particular presentation and take you to another presentation. So let me see if it is. Okay. I'll have to open it from my drive. I'll do that. Yeah. So I'll not give you too many things in the beginning itself, but I'll give you some examples. Okay. So let me see. This is visibility perspective. This is not very good, but let me just blow it up a little bit. Okay. So you see here. Okay. So you see here. This is my input space. So what is the dimensionality of the input space? Yes. What is the dimensionality of the input space? These are 4 points that are given to me in the input space. Yeah. What is the dimensionality?
1D.
1D, right? So what we have data is in 1D. And is it linearly separable?
No, sir.
So it is
No.
not
No.
linearly separable, right? All right. So now what we are doing is we are applying a transformation phi, which is defined here, right? Okay. Here, which is, I'll write it. So xy, oh, not this one. This is not this case. So this is what we are doing is we are going from d is equal to 1 to 2, right? Okay, your input space is one dimensional, and and you are going from 1D to 3D. Okay, all right. So, and in 3D, do you think that the data is linearly separable?
Yes, sir.
Yes,
Yes,
because we
sir,
can
if
find
I
a
consider
plane.
the plane.
We can find a plane. I mean, I'm drawing a line, but it is, I mean, let me draw it like a plane, right? So I can find a plane which will do this for you, right? So when I do this transformation, right, this is the idea, right? So what you do is, right, so okay, so let me take these 4 points again. Okay, so let me try to give you a simpler explanation to this. So this is 1 point, this is another point, and let me take this as a cross, right, and take this as a cross. All right, so this is in 1 dimension. Now suppose, right, so suppose this is x is equal to 1, this is 3, this is 4, and this is 8. Okay, all right. Now I have to add another dimension to this problem, right? So suppose this is x, now I make it y, and my y should be such that, right, any two of these points move up, right? Okay, all right, and the other 2 points remain where they are, right? So for example, if I choose my y in such a way that this point moves here and this point moves, say, somewhere here, right? So what do you have now in 2D space? So your new x is here, I mean the first cross is here and the second cross is here, and these two remain here and these two are gone now, right? So now what can you say? Is the data now linearly separable?
Yes, sir.
Yeah, so I can find a line which will separate the 2 kinds of data points, right? Okay, so can I find a transformation like this from x, or from 1 dimension to 2 dimensions, such that the points become linearly separable? So this is the whole concept about kernels. No, not the kernels, the mapping phi, right? So let me give you some more inputs. Let me see if I have it here, right? So just let me, yeah, okay. All right, so you see this, the same example. So let x1 be x1, y1, and x2 be y2 be two data points in a two-dimensional input space. All right, and I'm now considering the mapping x squared, y squared, and root 2xy. So what I'm doing is I'm converting this into a 3D space. Okay, all right. So what would be my x1 dash? So what is x1 dash? X1 dash is nothing but a transformation, which is this, right? Which is taking my x1 and it is mapping it to this. And what is phi x2? So I'll use a kind of a vector notation. X1 dash, X2 dash. All right. So you understand this? So if I apply the transformation that is given to me, X1 dash would be what? X1 squared, Y1 squared, and root 2 X1, Y1. You understand this? And then X2 dash would be how much? X2 squared, comma Y2 squared, and root 2 X2, Y2. So what I have done is I have applied phi, which is given here, to the 2 points. So x1 and y1 are the pre-images, and x1 dash and x2 dash are the images under the transformation phi. Now I am asking you to find x1 dash dot product x2 dash. So that means basically I'm asking you to find phi x1 dot phi x2, right? This is what I'm asking you to find. All right, and this is nothing but x1 dash dot x2 dash, right? So this is what I'm trying to find. All right, so how will I find this? So try to find the dot product of x1 dash and x2 dash. Do it. I mean, you do it on a piece of paper. Tell me what is x1 dash. Apply the dot product between these two vectors. Okay, do this. I'll also do it here along with you guys. Yeah. So what is x1 dash dot x2 dash? Write the expression.
x1, x2 plus y1, y2.
X1, no, write down the terms. X1 squared, x2 squared, plus y1 squared, y2 squared, plus 2 times x1, x2, y1, y2.
Yes.
All right. So now try to rearrange this one. Yeah. Try to rearrange this. It will be x1 squared into x2 squared plus y1 squared, y2 squared plus 2 times x1, x2, y1, y2. All of you are getting this? Component wise, you multiply and add. Right? That is how you do the dot product. So now I want you to rearrange this a little bit. Do some manipulation. So can I write it as x1, x2 plus y1, y2, right? All are scalars, plus 1 whole squared
Sir, how come plus 1? Isn't it just x1, x2 plus y1, y2 whole square?
No. Yeah. x1, x2 plus y1, y2 whole squared. Is that what you will get?
Yes, sir.
Yeah. So now what is x1, x2 plus y1, y2? It is nothing but x1 vector dot y1 vector whole squared. Is it not? What is x1, x2? If you see it here, what is x1, x2 plus y1, y2? It is nothing but x1 vector dot x2 vector, right? Dot product between the vectors in the input space. Can you see that?
Yes, sir.
Okay, so now what I am able to do is, I'll write it here. So this turns out to be x1, x2. I'm not writing one step in between, but that you understand. I'm writing it like this. So this is equal to nothing but x1 dot, all right? All of you understand this? So now you see what? The computation between x1 dash and x2 dash gets converted into computations between x1 and x2. All right? Are you getting this? So what I can write now, I can write, so let me use a, okay. So you can see it here, right? Okay. So what I'm doing now is I'm calculating the calculation that I showed you, that we did. It is this. All of you can check this. And this is nothing but x1, x2 plus y1, y2 whole squared. And this is nothing but x1 vector dot x2 vector whole squared. Okay. So in this case, what is my kernel? So this is basically what? This is phi x1 dot phi x2 is now equal to x1 dot x2, right, whole squared. Okay, right? So my kernel here is that kx1 x2, right, is equal to x1 dot x2 whole squared, right? So this is a special kind of a kernel called as the polynomial kernel. And its general form is x1 dot x2 plus d to the power of n, right? Where here n is 2 in this case and d is 0. All right. So are you able to understand this part? Yes or no? So we have been able to convert calculations in the feature space to calculations in the input space. So what we have done by doing this is that we have avoided the curse of dimensionality. Are you getting this? And this is called as the kernel trick. Okay, so please feel free to ask questions. Yeah, any questions? Anything that is not clear? Because see, this is the main concept, right, about kernels. Hello. Oops, I think, are you guys able to hear me? Because my laptop
Yes,
has
sir.
gone wrong, so maybe the recording has stopped. So I'll just check what is happening. Anyway, so any question?
Hello, sir.
Yeah.
So what's the purpose of finding similarity out here? Like, what purpose it serves us? in our whatever analysis we are doing.
So similarity, as I told you, if you looked at the dual formulation of SVM, right? Okay. So there, this x1 dot x2 was coming, right? So we are trying to do this in context of SVM. But in general, also you can think that suppose you are given vectors in a low dimensional space, right? Say a two-dimensional space. Now you transform this into a 10-dimensional space for any reason, right? Okay. And now you have to compute the similarity between any two pair of vectors in the new space, that is 10-dimensional space. So I am now telling you that those calculations can be converted into calculations in two-dimensional space. So does that help you or not?
Yes, it does.
Right? So in general also you can think, but here we are discussing in context of the dot products, right? Okay, because dot products are used in SVM. In the formulation of the dual, dot products are required, and you have to do it, I mean, n square times, right? Okay, so n is the number of training examples that you have, so you have to do it a lot of times. So, and if you do it in a high dimensional space, then you are increasing your computations, right? Okay, so to reduce the computations, we do this. We use these kernels, all right?
Okay, sir.
And this is a particular example of a polynomial kernel, right? There are many other kinds of kernels, as you will learn, right, as we go along, right? So you will learn those. All right. So let me take you to the next. Okay. So here, okay, let me see if there is any other example that I can quote. Oh, I'll have to go back to my original presentation, right? So this kernel things we'll discuss in detail, right? Okay. So just I'll have to open. Yeah. Yeah. So I'll take you to one of the slides now related to nonlinear SVMs. Okay. Okay. Right. So let me just a minute. Yeah. Yeah. Here. This I've discussed. So let me take one more example. Point. Just give me a minute. I'm not able to locate that particular figure. Just a minute. Yeah, you can see this one, right? Okay. So I'm not, I think I've not put that figure here. I'm not sure. So, okay, so you see this, let me put it in the presentation mode. Yeah. So you see this. So this is again a nonlinear boundary, right, between the two kinds of points. And then when we do the transformation, and this I'm just showing you a projection of that transformation, right? So you get a linear separable boundary, right? And then I showed you that this whole thing, whatever you want to do in the feature space, right, can be done using the kernels in the input space itself. So all the calculations in the feature space are now done in the input space. So let me, yeah. So this is what, yeah. So so what we saw just now was this, right? Okay, so you can generalize it even more. So, okay, you can write it as x dot z plus d raised to power p, right? So this D need not be 1, right? So this could be any number, and P, right? Typically an integer. In our case, it was D is equal to 0 and P was 2. So it boiled down to X dot Z squared, right? Okay. Now there's another kernel which is called as the Gaussian kernel, right? So you can see here, this is how you define at the bottom, you see how the Gaussian kernel looks like. Okay, so it is again the Gaussian function, e raised to power minus x minus z norm and by 2 sigma squared. So whatever is the formula for that you use. Okay, so let me give you some couple of things before we close this class. One more example I wanted to take up, but I am not able to locate that. Just give me a second. Okay, so let me, I'll take up example in the next class. So let me take one more case and show you some more aspects. Yeah. So if you see this picture here, okay, so do you think the data is linearly separable?
Yes, sir.
Yes, it is, right? So what I should be doing? Okay, what I should be doing? If it is, so data is linearly separable, this I can see. So should I go for hard margin SVM?
Sir, can you decrease the soft margin width?
No. I mean, right now, don't worry about the widths that are shown here. Don't worry about that. Okay.
No, but I do not think hard margin would be feasible, as that would be too.
No. So let's first do that, right? So what would be my hard margin SVM, right? It will be like this, right? And on this side, it would be like this, right? And this hard margin would be somewhere here, right? Okay, right? So the width is very small. So hard margin is possible, right? Because this data is linearly separable. But in this particular case, you can see that the width is very large that we have taken, right? This is too large and it incorporates so many points, right? Which could be wrongly classified, right? So you can see here, this is a solution which is having large training error. So what you should be doing in such cases, so you have a couple of options, right? One option is that you start
soft margin.
Sorry?
So we should use soft margin and drive vertical line.
What? No. Okay, I don't know what happened. Oh, just yeah. So what you should be doing is take the hard margin and keep expanding it, right? Move the boundaries to either side and stop when you have a threshold, when you have reached the threshold to the training error, right? So this is a particular case where you may have too many examples in the pipe, as we call it. So too many examples in the pipe is not a good thing, right? Okay, so we try to reduce that. So don't increase the margin by too much. Okay, so that is one is SVM. Now this soft margin SVM would work, right? So the options that you will have is that you have a soft margin which is having a training error of 10% and then another with 15%. So you have to see which kinds of again there will be infinitely many solutions for a soft margin. So you'll have to figure out which soft margin SVM you need to figure out, which you need to select. And the other thing is that should I be looking at, so the other option that I'm giving you is, should I be looking at nonlinear SVM as a solution to this particular problem? although you know that the problem is linearly separable. So should we burden ourselves with using nonlinear SVM in this case? So please think about this particular problem, right? Okay, and that we'll discuss in the next class. And another thing that I wanted to discuss with all of you is about the one more component I have to conduct. T1, T2, T3 are there, plus compre is there, but I need to conduct one more component. So I am thinking of a problem solving session where I give you one particular 1 or 2 problems and that you have to solve in 30 minutes and you upload it right after the test. It will be a subjective kind of a test, right? Okay, so that is one option. The other option is that I take a quiz of multiple choice questions and that you do, but I feel that in all the 3 tests you will have some multiple choice questions. So you have been solving multiple choice questions, right, already. So what option do you think we should, what should be the format of the 4th component that we have apart from compre? So you can give me inputs so that it helps me decide. Otherwise, I'll tell you in the next class.
Subjective one, sir.
Subjective one. Okay. So simple problem solving kinds of things. I'll give you a couple of problems and you will be able to solve them.